Hi, everybody. Thank you for the introduction. I don't know about pioneer. That makes me sound super old, so but I'll take it as a compliment. So it's good to meet you guys. I will turn on my chat. And if you have any questions, please feel free to jump in at any time and I will clarify. I tried to make everything pretty straightforward, but in case it's not, let me know. And then when we're done, I'm happy to answer anything you want to know, from what it's like being a woman in this field to getting involved with TSL, society, whatever. I'm an open book, so I'm happy to be of help, or choosing an advisor, whatever it may be. So I'm going to go ahead and get started. All right, so can everybody see the slides? So I'm Ann Campbell. I'm going to be talking about work I've done with my PhD student, Sarah Reed, who will be on the market this year. So you guys should petition your faculty to hire her. And Barry Thomas, who's also a faculty member at Iowa, who does a lot of work in transportation science. So you might know that name as well. So I'm in the Department of Business Analytics. We changed our name just a couple years ago. We used to be Management Science, but we really are Department of Analytics. A lot of different people doing things in machine learning, data mining, all those aspects. So we changed our name to match up with what we do. So the title of my talk is The Value of Autonomous Vehicles and Last Mile Delivery on the Urban-Rural Continuum. So that's a big mouthful. But I'm going to break it down and first talk a little bit about why you would consider autonomous vehicles for last mile. As introduced, that's kind of an expensive, important part of the delivery process. And then I'll get into the whole urban-rural continuum after that. All right, so you guys, do I admit the person to the waiting room? Okay, you got it. All right, great. So the idea of using autonomous vehicles for e-commerce deliveries, or for last mile deliveries, I should say, came about from just the increased level of orders through e-commerce. I think we all, particularly during COVID, order even more things online than we used to. You probably have some goofy examples of things you order online that you used to go out and buy at the store. Like I order dog food now. We all have things we order online. And so that's creating a lot of things that need to have that last mile that needs to be delivered to your home. So as an example, there's a study done in New York City in 2018 to try to get a handle on sort of how much is needing to be delivered to people's homes. And in that study, they said about 15% of households in New York City receive a package every day representing something they ordered online. And it does not look to be slowing down. Within that same study, it was projected to keep growing, with a projection of 68% growth by 2045. So doesn't look like it's slowing down. We've got a lot of packages that have to be traversed, that last mile that we're ordering online, that have to be delivered by someone to your door. As a result of all of these packages, it is a challenging situation and very expensive situation to deliver all of these packages. I like this article from Bloomberg where they say, in the final mile world, there's more work than you can handle, meaning it's really challenging to get all of these packages delivered with the resources and capacity that delivery companies currently have. And that is reflected by the demand we've seen over the last few years for delivery drivers going through the roof and creating higher raises and things like that. So all of these things people are being ordered require all of these things to be delivered, which puts a really big stress on all the delivery systems that currently exist. So it makes sense to start exploring other options beside the standard truck delivery driver model to see if there's other opportunities, if we're creative and look at different technologies, to see if we can help with the last mile problem created by e-commerce. So one of the options obviously is drones. A lot of people have been working on that. Some of you may be exploring the use of drones for package delivery. There's also the idea of package robots. I have a student who's defending in just a couple weeks who's doing his dissertation on package robots. But the challenge, so even though there's pros associated with drones and package robots, there are some concerns. One of the things is they can't really do what a delivery person can, meaning they can't go up the front steps. So I was trying to show that in the bottom picture. They can't open the door to the mail room in an apartment building. Drones can't do a lot of these things, and neither can package robots. There really still is a value of having a delivery person to be able to do those things. So the idea I wanted to start exploring is could we use autonomous cars or trucks and take advantage of this new technology that all these car companies are developing and pair it with a delivery person who would sit on board this vehicle and be able to make the deliveries. So first question is, would that be of value, right? I mean, how is it really any different to have an autonomous car or autonomous truck with a person on board be different than just a regular delivery truck? So we just wanted to start by looking into that question of what would be the value of having a delivery person just sitting and riding in an autonomous vehicle. Okay, so maybe think to yourself, what advantage could that create just riding in the car versus being the driver? Okay. So I was looking at what different companies were planning on and dreaming up for the use of autonomous technology. When I started looking at this, no one was really publishing any academic research in this area, but a lot of corporations were starting to kind of project different ideas about how you could use autonomous vehicles for last mile delivery, including FedEx, including UPS. But the one that was the most specific was USPS, so the United States Postal Service. They started looking at this idea of using self-driving mail trucks, which is kind of a funny thing to think of, but self-driving mail trucks, where instead of the traditional mail truck, you would have now the delivery driver now sitting as a passenger, putting mail in mailboxes as he or she goes down the street. So that was a good place to start thinking about what would be the value of an autonomous vehicle if USPS was thinking about doing this for mail. And what they thought would be the advantage of the autonomous vehicle would be while the mail person is riding in the vehicle, they could get ready for the next stop. So they could have the mail sorted out, ready to put in, so there wouldn't have to be that pause of finding whose mail belongs to this address, and they could be faster delivering the mail, okay? But we're not talking about delivering mail. We're talking about delivering packages like from Amazon that you guys order. And so it's not exactly the same thing as mail. So wanted to think about further, what could be the advantage with package delivery when the mail person has to get out of this autonomous car or truck and go to your door and make this delivery, or go up the stairs and drop it by your mailbox? What would be the advantage of pairing someone with an autonomous vehicle if they're going to have to get out and go to your door? So the idea was this, okay? And this was sort of the epiphany that kind of started this work, was what if the autonomous vehicle could drop off the delivery person, and the delivery person could have multiple packages on their person, like in a bag or in a carrying cart. And the delivery person could go deliver those packages on foot, maybe go to 3 or 4 different houses. And then the autonomous people could the autonomous vehicle could pick up the delivery person after they deliver the last package. Okay, so they're going to go to 3 houses. Then the delivery person is going to pair back up with the delivery person, the vehicle and person pair back together, and they can go on to the next set of houses. This eliminates the need for the vehicle to park, as well as it eliminates the need for the delivery person to walk back to the parking spot once the deliveries are made. Okay, so that's the big idea. Okay, so I'll do world's most jazzy graphics to explain this notion. Okay, so what's an autonomous vehicle? We can leave our headquarters. We can drive to the first stop on a city block, for example. The delivery person can get out and make, let's say, 4 deliveries. And then after they make the 4th delivery, they can meet back up with the delivery truck, drive to the next block, and repeat this process. And the delivery truck picks them up immediately when they're when they're done with their 4th delivery. There's no parking, there's no going back to the parking spot, and they can proceed through their deliveries in this way. Okay. Any questions so far? Go to a temporary loading zone. If it doesn't have a lot of time, it kind of depends how cities design the use of autonomous cars going forward. But that's a great question. We're kind of assuming there is a way that they can pick you up when you are done. That's a great point, that that's an assumption. So second motivation for exploring this area is, we said that some of the big things about using this drop-off pickup idea is we no longer have to have vehicles parking, and so we get that time back, right? So, and when you read about what's going on in urban environments, there's a lot of time spent, and you could say wasted, because it's not adding any value, for vehicles to look for parking places. On the right, we have a study from NREX, where they tried to look at the amount of time in various large cities in the US for parking. We've got numbers of 15 minutes down to 6 minutes in these 10 large cities to look for parking places, and Seattle represents the average of 9 minutes. Okay, so what's the big deal about the 9-minute parking time is that you're not just parking one time a day, right? If you're a delivery person, you're parking many, many times per day. So to try to get an idea of how many times per day, there was a nice study that came out in 2018 about London delivery drivers that we used just as an example. And in those studies, drivers are parking 35 times a day, right? So if you think you're a delivery person and you're spending 35 times a day looking for parking, and it's taking on average 9 minutes every time you look for parking, what do you spend a lot of your day doing? Parking, right? So if we can get that time back, we can make drivers, or now in this case delivery people, much more productive, and we can get many more packages delivered per day per person. Okay, so that was the sort of second motivation and drive behind looking at this. Okay. Any questions? Everybody good? Put it in the chat or holler out. Okay, so based on all these ideas, we created sort of the math problem, the academic problem that we're going to study. Okay, and we call it, it's a mouthful, the Capacitated Autonomous Vehicle Assisted Delivery Problem. That's our problem that's going to capture this aspect of having the autonomous vehicle do this drop-off pickup idea. Okay, so when we're going to minimize the completion of the delivery tour, we're really minimizing the time the delivery person spends from when they get on the vehicle in the morning till they make all these package deliveries and return back to the depot. Okay. So the key parameters to the problem that we really thought were important to be realistic in terms of the key factors to this issue is we had to think about what is the capacity of a delivery person, because right, we're talking about the vehicle dropping someone off, they're delivering packages and then being picked up again. There's a fixed number of packages that you could deliver. So we looked at that as a number queue, a letter queue to represent the number of packages. We are assuming sort of all packages are equal. We're not considering that Tian Cheng is getting a 45-pound bag of dog food like I get, where we could only really carry one, where all packages are the same. Okay, because you got to start somewhere, right? And then we consider a parameter F to model the time it takes for the delivery person to get off, get those packages ready, and go into the building. We also have a driving time. So when you're on board the vehicle, how long it takes to drive from vertex I to vertex K. amongst your customers, as well as walking times. Okay, so if you go to model this, because we've all taken IP kind of modeling class, I assume, the big decisions you have to make, I'm not going to get into the math too much, but just talk about the big decisions you have to make, is where is the delivery person going to ride on the vehicle, and where is the delivery person going to be on foot, walking and making these package deliveries to these home addresses. So if you think about where all your customers are, where am I driving and where am I walking on foot to make package deliveries? That's really the things you have to make as your decision variables. Okay. With that, our objective becomes this combination of using these X and Y variables. The first part, remember our D represented our driving time. So where the delivery person is riding on the vehicle, that time will be reflected by the left-hand side of the objective function. Okay, that'll take up part of their time of the day is riding on the vehicle. The other part of the time of their day will be time spent walking or unloading the packages off the vehicle to get ready to start walking. Okay, so that's sort of the second part of the objective function. Okay. All right, so if anybody has any questions, let me know. I'm just giving you sort of the highlights. Okay. Go ahead.
Can we go back to the last slide? What is sigma j, like set sigma, serve set sigma j? What is that?
Sorry, that's the set of customers that are being served together by one sort of group of customers that are being walked to. So in terms of Q, it's the set of Q or fewer customers that may be delivered to together before the delivery person is picked up again by the vehicle. Thank you, that's a great question.
Thank you.
Sure. Okay, so to Tianxing's question, that's sort of the M is the number of subsets of customers, which is dependent on the capacity queue. So if we can carry a larger number of packages, there will be more possible subsets. If you can imagine, if the capacity is 1, there's exactly n subsets where we deliver 1 package to each person. Okay. So the very first paper we did really only focused on the urban delivery side of things before we got to the rural to urban, but I think it's important to spend just a minute sort of talking about the first paper so you can kind of understand the leap from urban to the broader spectrum. So when we focus on just urban delivery, we're really wanting to understand if we had this model of the problem, what would happen if we tried to use this autonomous delivery model in an urban setting, and trying to get an idea of what kind of savings we could get from this autonomous model versus a more traditional model where there is a driver and the vehicle has to park, because really that's the comparison you want, right? You want to understand what's the value of investing in this autonomous technology, okay? So you have to start somewhere. So where we started was a grid network, because a grid represents a downtown, right? So as you see on the right, picture of downtown Seattle, where the last Informs is a perfect example of a grid network. Because we're on a grid, we're going to assume vehicles are going to travel in a Manhattan distance, having to obey the limitations of the grid. Okay, so in our very first effort in this regard, you have to assume something about where the customers are. Okay, so when we're going to try to make the comparison between using the autonomous vehicle and using standard technology, we said first, let's try to see what happens in terms of my completion time of my tour if there is a customer at every intersection of the grid, right? Whatever you're going to make, you're going to have some assumptions about where your customers are. So Very first example, we assume that there's a customer at every intersection of the grid. Okay, so I'll show that graphically with this picture. Okay, so this is a complete grid because there's a customer at every intersection. So you can think of this picture sort of representing there's an apartment complex or some sort of residence on every block or every corner of every block that requires one delivery per day. Okay, so we're going to use that as our baseline to really start understanding, in an environment like this, how much could this autonomous technology benefit us? Okay, so we first want to look at solving this instance to see what would the autonomous vehicle do, where would it go, how would it minimize the completion time of the delivery person's day. Okay, and what has turned out to be super nice about this problem is we can actually solve this problem in polynomial time. Okay, had no idea, worked out nice by exploring properties of complete grids. I admit it, sometimes you get lucky, right? Is what you find out when you look at complete grids is the shortest way to get through a complete grid is to find the Hamiltonian path, right? It's going to use the fewest number of edges possible. There's no ever benefit of taking more edges than necessary. So there's citations that talk about how to find the Hamiltonian path on a grid, okay? But the challenge that's still left us with is figuring out, okay, if I can find the Hamiltonian path through a grid, I have to figure out where is my delivery person walking and delivering packages, and where are they riding on the vehicle, okay? And what we found we could also prove is we could prove when, we could prove that in polynomial time you could establish what arcs you would use for walking and which ones you would use for driving. And what it really boiled down to is the size of the loading time relative to the difference between walking and driving speeds. Okay? That what we found out is the solutions really take one of two forms. They're either drive everywhere or they're drive as few places as possible, that you want to deliver as many customers on foot in a row as you can. Okay, what's the biggest number we can deliver in a row? It's Q. Okay, so here's an example in this picture where Q equals 4. So the optimal solution, if we have this inequality down here on the right, is I would ride on the truck till the very first customer. Then I would walk among the first 4. If Q equals 4, that's the most number I can walk between. Then I would get back on the vehicle and ride exactly 1 link. Then I would walk among the next 4, ride on the vehicle, walk on the next 4, ride on the vehicle, and so forth, right? It all depends on the trade-off between our parameter values, which of the two extremes is optimal. But we can prove in our paper that it's one or the other, that we either want to drive everywhere or it's optimal to drive as few places as possible, visiting as close to Q customers on foot before we drive 1 link, visit Q customers on foot, okay? But the key thing to see is, excuse me, I went the wrong way, is what happens when we, oops, there we go, is what happens when we compare this with what we get with a more traditional technology. Because remember, that's the question we wanted to look at, is what is the savings, okay? So the more traditional version of the problem, the one that's the current technology, we call it the capacitated delivery problem with parking, right? We can't really solve the VRP as the comparison because the VRP doesn't explicitly consider the parking time. So we've got to really look at incorporating the parking in the optimization of the problem. Like, what would be the minimum time we would complete the tour if we properly considered the parking in the optimization? So we consider this as a separate optimization problem. Unfortunately, even on a complete grid, this does not have a polynomial solution. We had to solve this as an IP, but we were able to solve it and get as a sample solution with these parameters as this picture. Okay, so these parameters are based on that study in London of driving time, walking time, loading time, and how many packages carriers were carrying in London. So we use those in some examples to demonstrate what the savings we can get is. Okay, so this is my favorite picture because I want you to sort of see what you can see for yourself in looking at the left side is the picture with the traditional technology where you consider parking. As you see at the top, parking is 9 minutes, and the capacity of what the delivery person can carry is 3 packages. The left side is the traditional technology with parking. The right side is with our autonomous vehicles. Okay. Do the solutions look pretty different in terms of the arcs that are chosen? Yeah, and we'll talk about that in just a second. But go to the bottom of the screen and look at the completion time of the tours. What do you notice? Which one's the longer one? Parking, right? Right? Parking's longer. How much longer? It's double, right? Why is that happening, that the parking time is double, okay? Or excuse me, the completion time is double. Let's take a look at the solution, see if we can figure out why, okay? So these boxes on the screen represent the places where the vehicle has to park. So how many parking places do we have in the left picture? We have 4, right? Parking time, we have 4 parking spaces or parking times. Each time we park, it costs us 9 minutes to find that parking spot. So that's 36 minutes in difference. But we're way more than 36 minutes longer tour time on the left than on the right. So why is that happening? Let's take a look at following the picture, okay? So in the traditional side with parking, what are we gonna do? We're gonna leave from the warehouse or depot, spend 9 minutes parking. We're gonna deliver a couple of packages. Then we're gonna walk all the way back to the parking spot. Then we're gonna reload and deliver 3 more packages and walk back to the parking spot, okay? Why do we not drive again to serve these? Because we don't wanna park again, right? So we'd rather walk back, reload, then park again. Then we're gonna drive way up here. Then we're gonna deliver to these 3, come back and reload, deliver to these and walk a decent amount back and reload. So you see, we not only get the advantage of no parking time, we don't have to spend all of this time walking back to the parking spot to reload. So all of that adds up to a pretty significant difference in the completion time in the left picture than the right picture, okay? So the question you should have is, did I find the most extreme example I possibly could to show you of the difference between autonomous and parking? And the answer is no. That across a wide set of instances of different sizes, we were able to find that with P equals 9, with instances all the way up to 100 customers, that this 50% improvement that I just showed you in the last picture, where the CAVADP was 50% of the parking solution, that was true across a wide range of different parameters and sizes of customers that we looked at. So what's the takeaway for parking with the average parking time of 9 minutes, right? On a grid that represents an urban environment, we could have a completion time of a tour be half the length as a traditional model that considers parking. So it's not a 3% difference, it's 4% difference, it's 50% difference. So we thought that was a pretty cool number to represent a real potential in the use of autonomous, right? We know there's some things not perfectly realistic with a complete grid, but that sure shows you it's a promising notion, okay? So what are some influences that can change the savings? As parking gets longer, we get a little bit more savings, 54%, right? But what was interesting is even when parking time is 0, we still get a 17% savings. So even though we don't have to spend the time parking, we still would have to spend the time walking back to the parking spot every time we make a delivery. So even just parking is easy to find in this very empty city, we still get a huge gain. Okay, any questions? Tian Cheng, you with me?
Yeah.
Navy.
I have a question actually. Let's say sometimes the driver needs a rest. So in our scenario, we are ignoring that, right?
In our scenario, what? They don't take a rest?
Yeah.
No, we don't have a break, but you would have a break if you were a driver as well in the baseline. So I mean, it would just be the same break presumably in both models. So you would still get, so instead of it'd be 20 minutes versus 120 minutes, right? You would just add that break in there, and it would still be a fairly close percent savings.
Okay.
Right? You might cut it down a little bit for that fixed factor, but you would still be adding it. You would have it in both, right?
Right.
Okay. So we're gonna switch over to the second part, which is the urban to rural, okay? So big takeaway here is that the autonomous technology looked very promising, that we could save 50% in the tour completion. So we wanted to dig deeper and look at extending this model. So we went back to those articles about companies that were looking at using autonomous technology. And one thing that kind of stood out to me was when USPS was looking at that self-driving mail truck, they weren't planning to use that in urban environments. They were planning to use it in rural environments, right? So we started thinking about, okay, well, what would happen with our savings? So we got this 50% if we were in a rural environment. Would the savings go away? Would they be even better? Is USPS designing these trucks for the wrong place? Or is the rural the right environment? Could that be even better? So that sort of motivated our second thought is, okay, now we did the complete grid to be a simple version of an urban environment. Let's think about how we could generalize the graph that we're solving things on and go maybe a better representation of an urban environment that's a little more realistic, and think about how we would modify it for suburbs and rural, and try to solve this capacitated autonomous delivery problem in these range of different environments. The question I really wanted to understand was sort of motivated by USPS was, would autonomous be better in the urban environments where we started? Are they about the same across the board, or would they even be even better in rural environments? So that was sort of the motivation to dig into this. So big changes as we go more general. Is we wanted to go to general graphs, so we're no longer on the grid. We no longer have a customer at every intersection, so we made our graphs much more general. And in doing so, we also wanted to incorporate as much real data, so we don't have to say, oh, your graphs are totally unrealistic, right? So we looked at maps. We used, and you'll see in just a minute, we used actual addresses and distances from mapping tools like OpenStreetMaps. We incorporated the fact that you might have one-way streets that change your walking and travel time options of going A to B, you might go one way, but B to A, you might go another because of the presence of one-way streets. And what challenge we didn't think about really could happen with one-way streets is it created the situation that driving could be slower than walking. And I'm going to show you an example that highlights that. Let's say you're considering going from customer A to B in the right-hand picture. Okay? You would really love to go this short diagonal that's on the left picture, right? But if we're dealing with one-way streets, that's not possible with a vehicle that's driving, right? If to go to A to B, you would have to drive this long way around, right? But if you're walking from A to B, we're still going to assume you can walk on the streets, and you can walk on the sidewalk of a one-way street. So you might be able to walk on the distance indicated by red, but to go from A to B to drive it, you'd have to take the arcs indicated by black. So in this situation, you could have that driving would take longer than walking. So you could have that if you're going to walk from A to B and have the vehicle pick you up, what could be the problem? Is now you might have to wait for the vehicle to get there. Okay? So that really induces the big change in the objective function is we're still minimizing the completion time of the delivery person's day. It's still made up of time on the truck, time walking, time loading the packages to get off the truck, but now depending on the solution that the optimization chooses, there might be periods of time where the delivery person is having to wait for the truck to pick them up, even without a stochastic environment, but because of these realistic travel times that we modeled into the problem. Okay. As you can imagine, when you get to this much more general version of the problem, we lose our nice structure, right? We're no longer this Hamiltonian path on a complete grid. Our resulting problem is no longer polynomial solvable. Okay? And as we talked about before, we have M sets of customers we can walk to. We have N customers. Now we have all these realistic distances. So the problem initially became kind of challenging to solve. So we spent some time studying it, figuring out valid inequalities. But really the breakthrough that made it more solvable, as you can kind of imagine from this formulation, is figuring out ways we can remove variables, remove sets from consideration. To Tian Cheng's question earlier, if there's a way we can remove sets from consideration of being ones that we would deliver to, that could really help our formulation become more solvable. So that's the one sort of breakthrough that I'm going to go over just a tiny bit. Okay, so here's the big idea. Okay, so let's say you have a delivery person already at node I, and you're trying to figure out the simple question, does it ever make sense for the delivery person to walk from node I to node K? So you're thinking about you're designing your sets. Would there ever be a set where if a customer is walking and is at node I, that they would continue on to node K? Okay. So if they walk to node K, that would take the time indicated by WIK. Okay, so it may be 10 minutes, whatever, to walk there. But we're going to compare that time to the time it would take to drive and get out and reload packages and go to customer K. Okay? Because that would be, instead of walking, we could drive, but then we'd have to get out and reload ourselves up with our packages. If it would be faster to drive to K and reload than walk there, we would never walk there, right? It would never make sense to walk there if it's better to drive and reload the vehicle. Okay, so the big takeaway would be, if I have this inequality, I can remove the idea of ever walking from I to K. Okay, what's the value of knowing that I'm never going to have to walk from I to K? Okay, we're going to represent that with what we're going to call the walking graph, which indicates all the combinations of customers where inequality holds where the walking is faster, okay, where I would consider walking between customers, okay, and we're going to remove the edges where this inequality happens in this direction, where we would never walk between customers. And what ends up happening is in urban environments, we can only remove a limited number of these edges. But in rural environments, there's a lot of places where it would never make sense to walk from this part of town to a customer on this part of town. It would always be faster to drive and reload than walk between these longer distances, right? So what ends up happening is, as we go from urban to rural environments, we're able to remove lots of these edges, and then we're only going to want to consider sets of customers to walk to on foot if they have edges, right? So if you think about in this rural environment, the only customers we would combine together in sets to walk to on foot will be customers that are connected via edges. Okay, so you can imagine this helps us dramatically reduce the number of variables in our IP. It reduces them some for urban, but dramatically more as we go from urban to rural environments. So that was sort of one of the things that you can say, just sort of like by using common sense, you can be thinking about things and come up with a way that can really improve your formulation. Okay. I'm going to talk just a little bit about some of the solutions. So the reason why we say urban-rural continuum in the title is because that is a term used by the U.S. Department of Agriculture to refer to sort of that range of urban to rural classifications. And they put these classifications on counties all over the United States. So that might be something useful to you in terms of building data sets. Sarah identified counties with each of these classifications within the state of Illinois. So if these don't ring a bell to you, these are Illinois counties, where 1 represents the most urban environment, and Cook County is the county where the city of Chicago is, to give you a reference. Okay, and so then they go more rural, less dense, less close to the grid graph. Okay. And then we created 10 instances for each county, where we looked at addresses and pulled 50 addresses from each county so that we could get an idea of the travel times, the proximity, the roads that would be taken in each of the different counties, and the walking times and the driving times. This little blue piece here is Lake Michigan. The red right here is Cook County, which is right on the water where Chicago is. So to give you a little familiarity. Okay. So we couldn't really find anything about parking time in a Continuum County on level 5. So we just made the assumption that the parking time gets faster as you go from urban to rural, where in the most rural, it takes 1 minute to find a parking spot. So we had to make some sort of assumption there, right? You definitely would not assume it takes 9 minutes in a rural community to find a parking spot. So we just made an assumption there, okay? So what we end up finding is even when we assume parking time is 0, due to that time walking back and forth to the parking spot, we get a savings of 18 to 12%. But the really interesting one is this one. Okay, so this is where we have the parking times, 9 minutes for the urban, 1 minute to the rural. And this is the savings versus that traditional technology of having a driver who has to look for a parking spot. Okay, and what do we get in the urban environment? Okay, by going from that complete grid with all of those simplifying assumptions to now this much more realistic model, our savings before that were around 50% are still around 50%. In fact, we're even better at 53%. Okay, but what do we notice happens as we go urban to rural environment? The savings go down, right? But in a rural environment, we're still able to get a 26% savings versus a traditional model of a delivery driver and parking. But definitely the savings are the best sort of in these more dense situations, and less savings as you get into more rural environments. And I have a couple pictures to kind of help you see some of the big changes that happen as we go urban to more rural. So I'll show you the picture for Cook County. So on the left is the solution for the parking problem. The orange is where the delivery person is walking. The black is where the delivery person is on board the vehicle. Okay. What do you notice is the difference between the left side and the right side? There's a lot more of the black arcs on the right representing the time that the delivery person is able to ride. And that's part of why this solution is 54% faster than the CDPP. And part of why you get so much savings here is we get very different choices between where the vehicle drives and where the delivery person walks between these two solutions. Okay, but here we have an example from Cumberland County. You see on this is the most rural county in our choices. And these two solutions look a lot more similar in terms of the use of the driving arcs, right? There's just not a lot of places you're going to walk in either one of these when you're in a very rural county. These blue flags indicate where the vehicle parks, but remember the parking in the rural county only takes 1 minute. There's a lot of time spent driving, just as there is a lot of time spent driving here. So that's why we get that less savings at about 26% here. All right. Last, going back to the USPS model, they talked about if the driver was on board, they could get the mail ready for the next destination. We also explored if there could be less loading time. If you are in a rural area and spending a lot of time on the vehicle getting ready for the next time you get off, maybe you could have those packages pre-sorted. And so maybe instead of 2.8 minutes to get the packages ready and get off, maybe it could be less than a minute. And if that was the case in rural environments, you could start to get very similar savings to what you can in the urban environment. So it looks like it may be even possible to get something higher than the 26%. All right, so let's wrap it up. We saw that the utilization of autonomous vehicle ideas reduces the completion time for all customer geographies from urban to rural. But we saw it was even better in urban environments than rural. And then the last, we might be able to get more similar savings in the rural environments if we consider a faster loading time in those situations. Okay. All right, so that concludes my discussion of autonomous vehicles for delivery. So I'm happy to answer any questions about that.